All right, let's begin the brainwashing process for you. From the very beginning, how to design such kind of basic op-amp. Yeah, so this is the highlight from Professor Randall Geiger, fundamental amplifier design issue, then from the single stage low gain, single stage high gain, all the way to gain boosting. How to enhance the gain, and then we can focus on the most popular two-stage op-amp design. So from the beginning, how to design the basic amplifier. All right, this is the first page to wash your brain. What is an op-amp? Okay. What is the so-called op-amp to your understanding? Yeah, maybe for circuit symbol, it looks like this. It has two terminals for input. Yeah, we call it inverting input and non-inverting input, or simply a positive input, negative input, and one output. That's it. That is, I guess, what you learned from your microelectronics. That is the textbook definition. That means this is some kind of voltage amplifier with very large gain. Yeah, very high input impedance, very low output impedance, because all in voltage domain. Okay? Yeah. And this is the overall structure, differential input, and single-ended. Only one. It means single-ended output. Yeah. But before we redefine the op-amp for you, we can think further. Why we would like to apply such kind of operational amplifier? What is they will be used? This is the usual case. It means what? Op-amp seldom stand alone, seldom operates by itself. No. It is only a building block for the others. Okay, so usually for the op-amp application, we put op-amp here, and through some kind of negative feedback to stabilize the overall, not to stabilize, but to enhance the performance of the overall system. That is the usual case. All right? And why we need such kind of closed loop application? Simply because according to process variation, this gain could be very large, but also with very huge variation. Yeah, for example, if you have some kind of speaker driver, right? If the gain varies too much, maybe 50% of the mobile phone, you say, the sound is broken because it's too loud. And for 50% of the mobile phone, you say, hey, it's too small. Yeah, the volume is too low. I cannot hear the voice clearly. So how to control the gain after fabrication? How to get stabilized enough gain? Okay. We need the help of this, because according to that is so-called feedback network. All right, and this is the feedback factor. Okay. Anyway, I think you learned already. Maybe chapter 7 from Smith, Cedar Smith's microelectronics, blah blah blah. After very simple derivation, you can get this. If the gain is large enough, then finally the overall gain after feedback will be 1 over beta. It means what? Only if beta is stable, then the overall gain will be stable. Maybe you will be curious why this cannot be stabilized and beta can. Right? Why beta can be stabilized? Simply because for such kind of feedback network, we apply the same materials, the same kind of devices. For example, R1 and R2. They are of the same type. Okay? So if you do good enough layout, yeah, common centroid, first order, second order, blah, blah, I don't care. Yeah, only if you pay enough attention to the layout for the same materials, I promise you. Yeah. to achieve not only 1% or even less, 0.1% in accuracy is totally possible. But how about this? Never mention about 1%. Never mention about 10%. I promise you, usually 20 to 30% in variation, and you have no way to control it. Or even the larger gain, the more variance. Sometimes maybe even 50% to 200, 300%. Okay? So this is the reason why we don't apply op-amp individually. No, because it gets too much variation. To stabilize its performance, we need negative feedback to get this. We can promise you a happy enough future. Okay? So, op-amp is usually applied in such kind of negative feedback loop. And the only requirement, just like here, high enough gain, as high as possible. Okay? So, the most fundamental requirement for op-amp is very large gain. And then what? Yeah, maybe you will say, to make the feedback overall gain insensitive to the variation of your op-amp. Okay, yeah, anyway. And also, I told you already, what is the most important idea? What is the most important slogan for negative feedback? I told you again and again. The amount you reduce your gain, you sacrifice your gain. How much you sacrifice your gain were used to enhance all the other parameters. Okay? For example, if your original gain is 1,000, you reduce it to be 10, then you sacrifice 100 times for your gain. Then congratulations. For all the other parameters, the bandwidth, the linearity, the error, all of them will be improved by 100 times, almost. That is the power of negative feedback. So we can enhance the linearity. What does it mean? We can reduce the non-linearity. Okay? Anyway. But if you look at the specification of commercial op-amp, right now we still have a few. I cannot say quite many, no. A few standalone commercial op-amps. If you look at their specification, I promise you, not only this, more than 20 or 30 specifications. Okay? Only for the terminologies, 2 pages. What is terminology? Definitions. The names. Okay? We call it terminologies. That is the formal name for the name. For the specification anyway. Okay. Oh, for such kind of commercial products, you will see a lot of the others. Oh, large output swing, large input range, good high frequency performance, fast settling. Whoa. Okay, anyway. Okay, more than 10, even more than 20. So, what do you need? What all those properties, characteristics are really needed for your op-amp design? For commercial part, for the catalog. Japanese say catalog. So some of the Chinese also say catalog. That's it. For the catalog, you can see, wow, those mentioned or not mentioned, all of them listed. Okay, because again, they are general purpose op-amp. All right? But anyway, for your own design, usually we have specific purpose op-amp. The op-amp is designed to fit your own application. It doesn't need to please all the other applications. Only specifically designed for your own application. That's it. One for one. That's it. Not one for many. All right? So we only choose from those many when necessary. and forget about the others. So usually only 1 or 2 or 3. That's it, good enough, no more. Again, don't do any kind of over design. That is really dangerous. Money wasting, time wasting, right? And it will be risky for your own future because you both focus on money, on budget very, very much. Okay? Do a good enough design. It's good enough. No more than that. More than good enough means really bad. Okay? Not only bad for your future, but also for your companies. Okay? So avoid over design. That is the first lesson you need to learn. So let's go back to check. If we would like to apply our op-amp in such kind of negative feedback loop, what kind of possibilities? What kind of possibility? Because from the very beginning, you learned from microelectronics, not only microelectronics, but also from your physics, fundamental physics, right? Usually, we learned voltage first, and then we apply voltage to resistor, then we get current, okay? So that is voltage oriented learning process. Students, engineers focus very much on voltage instead of current or the others. But I need to warn you again, for CMOS analog IC design, we focus on current very much. Usually, current is the input, then we generate maybe voltage for output or something. We call it stimulus, okay, 激发源. Anyway, stimulus. The stimulus is usually current instead of voltage. But anyway, because according to our traditional education, most of the students, engineers are familiar with voltage. So from the very beginning, you learn this for op-amp. But as you know, 2 main properties, either voltage or current. So for the input or output 2 by 2, voltage or current, I mean. So totally, we have 4 possibilities. That is the original typical op-amp. But if the input is voltage, output is current, we call it what? Just conductance. Okay, again, according to circuit theory, we put output over input. So right now, the output is I, right? And input is V. Oh, that is the reverse of resistor. We call it conductance, right? Right? A change means what? Input and output, they are different. They belong to different port. Okay, that's it. If they belong to the same port, then we don't have the chance. We have only conductance. For example, if you apply the voltage to the resistor to get the current, then the input and output happens at the same port. Okay, then we don't have chance. That's it. That is fundamental terminology. Yeah, I'm not your teacher for circuit theory, but I hope I can refresh all your mind. Anyway, on the contrary, if the input is I, the output is V. Oh, that is resistance. So we call it resistance amplifier. Okay, and if all of them are current, then we call it current amplifier. That's it. Okay, but I wanted to ask you, in the past, you put this into the loop. How about the others? Did you learn anything about this? Because totally we have 4 types, right? For the input, for the output, 2 by 2, totally 4. We always focus on this. Just like in the past, again, we were told, oh, our earth is flat. Don't sail to the end of the world, otherwise you will fall down to the hell. Don't believe in that. Ridiculous, right? So again, even in the past, we only learned this. But why not try the others? Allow me to show you. What type of op-amp is required? Can be functional. This is proved. But how about the others? Before we do any kind of trial, before we try anything, except In addition to, not except, in addition to the traditional op-amp. Okay? Let's think about the properties, the characteristics. You can see for VV, voltage op-amp. Voltage input means what? To reduce the so-called load effect. Right? We hope the input resistance is infinite, as high as possible. Right? According to Thevenin equivalent circuit, that is, Thevenin equivalent 带为拧等效电路. Okay? Yeah. So we hope for the input, the resistance should be sky high. And again, for the load effect, we hope we push all the voltage to the output. So we hope our own output resistance is 0, as small as possible. Okay? According to, again, Thevenin, that is the output. If you are the driver, then we hope this is equal to 0. If you are the load, right, the input stage, we hope this is infinite. That is the very simple idea. But on the contrary, if both are current, then we need to apply Norton equivalent circuit. 诺顿等效电路. It looks like this. If you would like to, as a driver, if you would like to deliver all your current to your load, this one should be infinite. Your own output resistance should be as large as possible. Oh, it is totally contradictory to your voltage counterpart. They are counterpart. They are not friends. Okay? But you see, how about the input? Oh, for the input resistance here, right? Hopefully, this is 0. Why? Because you can absorb all the current in. Never mind how much the RO is. So for the input, hopefully it is 0. Wow! See? They are totally contradictory to each other. For the point of view of current, the input resistance should be 0. But for voltage, it had better to be infinite. Okay? Wow! They are totally contradictory to each other. And in between, just do it by yourself. Anyway, well, in properties, they look totally different. But be brave. Just row your boat all the way to the end of the world. You will find America. Okay, let's do it. Yeah. To differentiate all 4 types, we modify the circuit symbol for you. If I cut it, it means current output. Okay? If I short it here, it means what? Current input. Because we hope Ri is 0. Okay? Yeah, for your reference. And then, if you look at one of the typical application for op-amp, we call it inverting amplifier, right? You learn it already and you derive, and finally you get this. Oh, congratulations. Why we call it inverting amplifier? Because the gain is minus R2 over R1. That's it. And again, R2, R1, that is composed the beta network. Okay, and I told you already, because usually they are of the same types, then we can match the performance, the properties after fabrication if you do a good enough layout. All right? Yeah, anyhow. So, I don't care who you are. I mean, I don't care what kind of component you have here. For the overall circuit, we only hope V out over V in. The voltage can look like this. And if you apply the traditional, typical op-amp, the only requirement is the gain is high enough. Then you will get this. That's it. It's okay, right? Let's go for the others. Yeah, anyway. Whoa. See? Let's try. Let's roll our boats to the end of the world. This is conductance amplifier, right? Yeah, voltage input, current output. Yeah, or current input, current. I don't care, I don't mind. Let's try this first and check the result. All right. Oh, to be brave, to apply new device into the feedback loop. Wow, 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 okay, wow. Wow, finally. Again, if the gain, I mean change conductance, is high enough, okay, high enough, it means this will be infinite, right? So this term will be 0. We get this. Congratulations. Okay? If you are curious, this is second type, right? You can apply the third type, the first type, I promise you. Only if the gain is high enough, you still get the same thing. See? See? So, the first I would like to wash your brain is, what is the definition for op-amp? Definitely, the input and output need not to be voltages. They can be either voltage or current. And why? I would like to expand your territory. Yeah, because in the past, we learned everything typically, traditionally. So we will get some kind of narrow-minded. We only focus what we learned from the past, from the history. But we don't look out. The outside world actually is much wider than we can expect. So just try it. Nothing to lose. Right? If you try it and then, wow, this one is no good, then forget about it. Right? But before trying, don't say it is impossible, because again, what is the difference? See? If it is op-amp, then RO, in theory, is infinite. But right now, it is cut. It is current output. The RO is reduced from infinity to 0, but we still get the same thing. No worries. No worries. Okay? Just do it. Just try it. Be brave. So, again, right now, we know. Never mind that is voltage or current. Only if the gain is large enough, then we make the same output for you. All right? So it means what? Never mind you apply this, or that, or that, or that. All of them can make it. Only if the gain is large enough. That's it. Okay? So, what is the fundamental requirement for op-amp? High enough gain. I don't care what type of input, what type of output. I don't care. Only if the gain between output and input high enough, then they can do their jobs for you. Okay? Yeah, a large gain is needed, is required. So, allow me to reword the definition. 重新定义. Yeah, definition for op-amp. Amplifier? What is op-amp? Amplifier. Never mind what kind of amplifier. With very large gain. Only that? Oh, because right now, we broaden your mind from voltage to any kind of possibility. Oh, okay. Never mind voltage or current. But both of them, all of them, look similar to each other, because you have differential input and only single-ended output. Does it necessary? Okay, let's go further. Does it necessary? Go further. Yeah. For such kind of inverting amplifier, if this is inverting amplifier, and that is non-inverting amplifier, okay? For non-inverting amplifier, actually, for the op-amp, the so-called op-amp, it needs to connect to the output, connect to this node, and also, so it needs 3 terminals. But how about the inverting amplifier as a black box? Actually, for the others, they only need to know this node and that node. That's good enough. They don't care this. Inside the box, who cares what? All right? So it seems possible that maybe we don't need such kind of 2 input and 1 output. Maybe. We can reduce it. I mean, hey, don't tell me. Wow, I can, again, make it as a black box. So only focus on this and that. No. In this way, where to apply your V in? You still need to tap out for V in, right? So for non-inverting amplifier, you need at least 3 points, 3 nodes for connection. But for this one, we only focus on those nodes. Good enough. Yeah, I mean, for all the others of the whole circuit, they only need to know this node and that node. They don't care about what's inside the black box. Okay? So sometimes it needs 3 nodes. Sometimes it only needs 2 nodes, blah, blah, blah. But sometimes it needs 4 nodes. Yeah. That is case by case. So it means for inverting amplifier, for the whole circuit, actually, we only need 1 input and 1 output. That's it. I don't care the others, as you like. Right? So, in theory, we can reduce this to that as a black box. Only if this one can provide large enough negative gain. That's it. Okay, so it means what? The input becomes single-ended instead of differential. Right? Yeah, it is possible. But sometimes we have such kind of fully differential. It means both input and both output should be differential. Yeah, it is it's used quite often for on-chip application. But for off-chip, I mean commercial parts, commercial products. Actually, they seldom touch such kind of fully differential op-amp. Okay? Yeah. Anyway, that is widely used for on-chip application. Yeah, seldom available in commercial products. So again, what is the definition for an op-amp? Because we told you again, amplifier with very large gain. That is the first requirement. And then, for the input, it could be differential or single-ended. Output again, it could be differential or single-ended. Wow, we get much more freedom, much more flexibility than before. Yeah. So, for those two, who decides it? Your application. Again, how many for input, how many for output? Who knows? It's up to your application. It's not instead of you or me. No. The application decide what does it need. Okay? And you guys select the best one for your application. That's it. Okay? And then let's go further. Yeah, how to design such kind of very flexible op-amp. Single-ended, differential, yeah, current or voltage, who cares? Anyway, from the very beginning, let's have a look at such kind of single-stage, low-gain op-amp. All right? Single-ended input and single-ended output, and this is for differential. Okay, yeah. And again, this is what we mentioned moments ago. Oh, don't forget, what is the original circuit in the past? We have this. Right? Inverting amplifier. And what is the result? Don't forget, never mind what kind of op-amp you apply. The result needs to look like this. Minus R2 over R1. That's it. That is what we required. I don't care what kind of device you have here. Okay? I only concern the output. The output gain needs to be like this. Okay? The voltage gain. So let's go further. Yeah, if you apply such kind of single-ended input and output, very simple. amplifier. Then after derivation, okay. Anyway, allow me to show you this. That is final result. See? That is what you need. And for the others, you can check they are something like offset. Even for your op-amp, you still have offset. Okay, but anyway, you have positive one, you have negative one. Actually, it is possible for you to cancel it with careful design. Okay, so if you cancel the offset, then bingo, you get exactly the same thing you learned from microelectronics, but with much simplified structure. Okay, that's it. But how to compose, how to construct such kind of single-ended, very simple, single-ended op-amp? This is what you learned already. Common source amplifier. That's it. Right? And again, this is your input. Through the help of input transistor, we convert the input voltage into output current. Right? And then multiply your output current by output resistance. You will get Vout. That's it. Very simple idea. You don't need to derive. You just think. Then you can get what's the outcome. Okay? But anyway, that is an idea. However, how to realize such kind of current source? This one, right? Simple current source. You apply constant bias voltage to the gate of this one to make it provide, in theory, constant current for this one. That's it. Okay, so this is basic structure, and that is the practical implementation. And then, you can derive. But for me, again, what I told you. First of all, you convert V in into I out. Right? So what is I out? GM V in. Right? And then, what is the V out? By R out. But if this one is perfect, then you have only RO here. Right? That's it. What is RO? The inverse. That's it. So what is the gain? GM by GO. Okay? But we need to concern, that is a very easy idea. If you are interested, you can do such kind of analysis, right? Calculation by applying such kind of small signal equivalent model. Finally, you will get the same thing. Okay? I have no time. I'm a busy guy, so I only estimate what's the result. And usually, you need to pay attention to the bandwidth, and bandwidth is seriously limited by such kind of parasitic load capacitance. Anyhow. Okay, and again, what is the total output conductance? Because this is perfect. Then your output conductance, because they connected in parallel, right? So the overall output conductance is your conductance plus his conductance. For impedance, we have, right? And for conductance, congratulations. That's it. And what is output resistance? 1 over this. Okay? And that is output conductance, output resistance. And we still need to multiply by transconductance. Congratulations, you get this. That's it. Okay? I don't need to derive anything. I just think, then I get this. Bingo. Perfect. Okay? And if for anyway, train yourself to behave like this. Don't derive, just think. Okay? Good, very good, very efficient for estimation. If you're lucky, you will get the same thing. Just like moments ago, I think I solved for you. Okay? But this is such kind of ideal case. right? Basic choice. But for practical implementation, what is the difference? No ideal current source. So you have that. So what is the difference? You still convert your input by M1. So you still get the same GM1. Okay, if I have 1, that is for M1. That's it. Okay? And then what is the output resistance? The same. The reverse of output conductance. But for output conductance, right now you have 3, right? Output conductance here, output conductance. All of them need to be summed up. Okay, so haha, GO1, GO2, and SCO. That's it. You get it. Within seconds, you make it. You don't need such kind of very complicated small signal equivalent model. It simply wastes your time. Okay? Just think. Good enough. And let's go further. Because, from fundamental circuit theory, if you have something like this, it should be if we are similar to low pass filter. Yeah, first order low pass filter. Right? So what is the bandwidth? Oh, okay, let's go further. What do you learn from fundamental circuit theory? It looks like that. That is a normalized form. 正规化的格式. Yeah. That is the DC gain over 1 plus S over bandwidth. If you try to match your expression to that, then congratulations, you will know here is what? DC gain. And what is bandwidth? There. Okay, that is bandwidth. That's it. Congratulations. Okay? Yeah. Anyway, so according to the analogy, 相似性, okay, or the so-called similarity between your form and the normalized form from fundamental circuit theory, we will know, the DC gain is this, okay, and the bandwidth is that. And then we have, again, gain bandwidth product, okay? Yeah, AVO by bandwidth, then G out will be cancelled. You get this. Wow! What does it mean? Again, moments ago, or in previous, in the morning, I told you how to enlarge your gain. Usually, the cheapest way is to increase your output resistance. It means to reduce your output conductance, right? By that, you can increase your DC gain, but at the same time, you will decrease your bandwidth. Okay? So, for gain bandwidth product, you can see no GO or RO here. It means what? Never mind how hard you try to increase your output resistance, you can only increase your gain, but nothing you can enhance for your gain bandwidth product. It stands still. 它站着不动，纹风不动。Nothing you can do for your gain bandwidth product. So again, it means what? When you increase your gain, usually you need to sacrifice your bandwidth. Okay? That is so another ugly truth. 丑陋的现实. That's it. Yeah. For the same structure, never mind how hard you try to increase your gain, you need to sacrifice your bandwidth. Never mind how hard you try to increase your bandwidth, you need to sacrifice your gain. That's it. Okay? So you need to do trade-off for your design. Okay? Compromise. You need compromise gain with bandwidth. That's it. Okay? So even though all those are really simple equations, but you can learn something by thinking instead of derivation. By derivation, if the student get this, get that, They're curious. What's for? what can be used for with all those equations? So thinking is much more important than derivation. All right. And for op-amp design, gain bandwidth product and DC. DC gain and bandwidth should be the most important two parameters. If you combine them, you get gain bandwidth product. Okay, that's it. So for your own design, we have parameters right now because DC gain. Why we call it DC gain? Oh, very simple. See? Because S equals J omega. Yeah. And it means 2 pi f, right? That is the frequency. So if frequency means 0, this is 0. Oh, you get that. Congratulations. That is what the so-called DC gain. For your frequency response, it looks like that. That is the frequency. F or omega, I don't care. This is radian frequency, and this is frequency, okay? And AVO here, the DC gain, exactly. But usually we don't plot it in linear scale. Instead, we plot it in log scale, okay? Log scale here, log scale there. Yeah. Anyway, for your own design, what is the important parameters? You need to, how can I say? If the parameters are good, first of all, you can have a better insight into their, not only performance, all those two, I mean DC gain, bandwidth, they are according to performance. But if I only show you, the gain is 10,000 and the bandwidth is 1 megahertz, blah, 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 then you won't have any idea what the circuit look like, right? If I only show you the gain, the bandwidth, then it's really hard, especially for new designers, to think, wow, what on here you have for the circuit. All right. Anyway, if I show you the circuit, wow, then for the new designers, they are really hard to imagine, to guess how good the performance will be. So that is some kind of difficulty. Yeah. To have better understanding of the circuit or to have a better understanding of the performance, they are a little bit contradictory to each other. That's it. But, and again, I'm talking about to make your design easier, to make your life happier. All of us hope we will know W over L, W over L, and how much the CL will be, right? Blah, blah, blah. But even I show you this, I will tell you, well, this is maybe 1 or maybe 3 micron over 1 mile, and that is 1 mile over 1, blah, blah. And this is 1 microfarad. That's it. If I offer all the detailed specifications, then what? Tell me how much the gain will be, how much the bandwidth will be. All of you will think, wow, I have no idea, right? Oh, so there is a hard boundary about the performance and the detail sizes, bias of the circuit. Yeah, anyway, so that is what Professor Geiger's concerns very much about the parameter domains for your own design. We hope you can get not a good understanding not only for the performance but also for the circuit itself. And also, I told you already, most of the time goes for optimization. So he hopes all those parameters can help designers speed up the optimization, blah, blah, blah. Okay, anyway, yeah, I will show you the design of freedoms. So consider such kind of fundamental op-amp structure. Yeah, I thought for you already the performance. I saw the performance. I guess the performance for you Okay, without any derivation. Now we have this and DC gain, again bandwidth product. Okay, anyway. Yeah. So Professor Geiger told this small signal parameter domain. Okay, so we have GMGO. That's it. The most important. But because load capacitance is some kind of parasitic, okay, it is not designed by us. Yeah. After your design, you will get this. They are parasitics. So our design will focus on GM and GO. Okay, that is the small signal parameter domain. Yeah, we have 2 degrees of freedom. 你有2维的自由度. Okay, and then, yeah, for such kind of small signal domain, you will know the performance immediately. Oh, the DC gain, and that is the gain bandwidth, blah, 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 blah. Okay, but it's really hard for you to guess the real circuit, the real implementation. What the real implementation will be. I mean, it's really hard for you to guess. Even for me, I have no idea how to guess that. Okay, so let's go for the other possibilities. Yeah. As I mentioned, to please you, to help you the most, I simply provide you how much bias current here and how large M1 is. Oh, you will be really happy, right? But after I provide you this and that, most of you won't have any idea about the performance. What is the gain? What is the bandwidth? No idea. You need to derive. If you ask me, to be honest, I need to derive in this way. Okay? Anyway, here we W over L, the sizes, okay, the aspect ratio and bias current. Yeah, we also have 2 degrees of freedom, this and that. The same as the small signal design domain. Okay? Now you can achieve the same thing. Yeah. If you are curious, you can derive it. Wow. Oh, see? GM look like that. Okay? And how about GO? Wow. Anyway, you can combine this GM and GO to achieve your gain bandwidth product and your DC gain, blah, blah, blah. Anyway, you can derive it, but according to the expression, wow, it is really complicated. It has square root here, it has square root there. So for optimization, this is really no good. Because for such kind of square root calculation, it takes a much longer time than what? Than simply multiplication or division. Because according to Taylor series expansion, okay? Yeah, how to have a square root of something? Usually we have, according to calculus, we have a lot of expansion, series expansion. Anyway, many issues like that for approximation. Okay, anyway, it's really time consuming. If you would like to do any optimization with this, it will slow down your speed very, very much. Okay? Yeah, anyway. So, right now we have 2, right? Small signal parameter domain with those 2, then DC gain bandwidth product. Look very neat. Okay? Very simple, very clear. But it's really hard to see what the circuit looks like. If you would like to look what the circuit looks like, I offer you the W, the L, the IDQ, right? Then, it's really complicated for your DC gain and gain bandwidth product. It's really difficult for optimization according to calculation. Yeah. The main concept for Professor Geiger is to optimize the circuit automatically. It means you compose some C++ program or MATLAB program to do optimization instead of hand calculation or simulation. Okay, hopefully. So this is good for you to understand the circuit, what the circuit looks like, but it's hard for you to guess this and that. and also very slow for automatic optimization. All right. So, but before we go further, yeah, Professor Geiger would like to do you another favor. All right, to separate this and that by two terms. The first term is process dependent. It means it is decided by TSMC or UMC, not you. As a designer, you can only decide the second term. Okay, not only for DC gain, but also similar for gain bandwidth product. This is process dependent, and that is, yeah, design dependent, architecture dependent. Okay? Anyway, anyhow. And then, Professor Geiger would like to provide you alternate parameter domain. I myself was also curious what kind of parameters he would like to have. Power and overdrive voltage, or the effective bias. Okay? It means VGS minus VTH. But why? Okay, allow me to show you. Because for DC gain, it looks also very neat. 非常的简洁. Very, very simple. And how about the bandwidth? Oh, again, much simpler than square root. Wow, that is too hard, right? Yeah. Those two, they are very simple for calculation, for automatic optimization. But you will be curious with power, right? And, yeah, overdrive voltage. How can you? That is very easy for you to know the performance. But how about the circuit itself? Okay. Again, process dependent and architecture dependent. Anyway, 2 degrees of freedom, similar to each other, right? And then, what's this? Okay. Yeah. All right. Professor Geiger is good-hearted. He helped you to derive. Oh, very simple. With power and excess voltage or overdrive, blah blah blah. Okay, you can derive your bias current and your aspect ratio very easily. Okay, piece of cake. Yeah. Anyway. So, that is only for brainwashing. Okay, but for the rest of 300 pages, I will skip such kind of parameter domain because why? Because automatic optimization till now is still our dream. Yeah, it never be true. Maybe into the future it is possible, but right now it's only some kind of fantasy. Yeah, 梦想. Okay, it's not true. So I wouldn't like to waste your time, but I would like to share the interesting idea from Professor Geiger with you. Okay, yeah. Anyway, for such kind of design space, I don't care what kind of parameters you have, right? But for your design, you need to have some kind of constraints, 限制. Under different constraints, yeah, the same parameters will look totally different from the others. Okay, so for example, under such kind of situation, you can see gain bandwidth is increased linearly with IDQ. Okay, and then under the other equation, it looks like that. Okay, and again, well, it is constant because IDQ doesn't exist in the equation. So gain bandwidth product is irrelevant with your IDQ. Wow. Anyway, you can see for all those equations between gain bandwidth product and IDQ, you can see, this is a linear increase, and this is quadratic increase, and this is independent. Well, which one is correct? Again, all of them. are correct, but under different constraints. OK， 它们全部正确，只是限制不一样。That's it. OK, so what does it look like? Depends on how you explore the design space. If you fix this parameter or that parameter, then you will see different results. That's it. Okay. All right. Enough is enough. I wouldn't like to bother you again with such kind of design parameters. Yeah. But in the future, if your company or your supervisor would like you to write some programs for such kind of automatic optimization for your op-amp design, your circuit design, then you need to remember, today I show you all those ideas, and hopefully you will choose the recommendation from Professor Geiger. What does that? Huh? Oh, that is really bad. Yeah. Hopefully you will choose this one to speed up your process. Alternative. Okay, where is that? Not small signal parameter domain. Okay? Not natural parameter domain. No. Yeah. Not this. Okay, hopefully you will choose in the future. The third one. Alternate parameter domain. That's it. With power and VEB. Okay? Anyway, let's go back to real world. Without automatic optimization, who cares what kind of parameters you will use? We will go to the bottom to design the overall circuit with good enough I bias, with good enough W over L. That is for single stage low gain amplifier. It looks like this. Yeah, that is the fundamental structure. Yeah. Some kind of observations to help you, especially for new students, new engineers. Usually for such kind of single-ended input and output op-amp or amplifier, it is usually some kind of common source amplifier. The gain usually descended, not too high. Okay, not too high. Yeah. Inherently, it is some kind of transconductance. Convert input voltage into output current, then by RO to get the output voltage. Yeah. So we hope the output impedance is high enough to get good enough output voltage. Yeah. And again, alternative parameter domain is more useful to speed up the optimization, but forget about it. Yeah. That is for only our dream. Okay. But for real life, you need to do the design by yourself without any automatic optimization. Okay. Yeah. So right now, we briefly introduced the concept for such kind of single-ended input. And how about the differential input op-amp? Yeah. We can learn something from the single-ended input because it's really simple to analyze. Just like moments ago, I guessed the performance for you. I mean, with such kind of single-ended op-amp. Okay? But how about the differential one? It's much harder. But later I will show you a systematic way. Yeah. How to estimate the performance of such kind of typical op-amp through the help of such kind of very simple single-ended input. Single-ended input amplifier. Later I will show you the secret. Okay? So you can see the performance of such kind of traditional one can be directly determined from this one. It means what? Only if you have good understanding about such kind of very simple single-ended amplifier, you can guess, you can estimate directly the performance of the traditional one. Okay? Later, I will show you how.